Hello friends, so today we are going to solve 5 questions, and all these 5 questions will be from projectile. And so the first question is, one second. Okay, so the first question, and it states that a ball is projected with a speed v0 from the ground toward a vertical wall located at a horizontal distance L. At what angle of the projection should the ball be thrown so that it strikes the wall at a maximum possible height? So this is a basic question. And so we can just draw the basic figure according to the question. So suppose this is the wall, and the projectile is launched, suppose, from point A, and this point A is at a distance of L from the wall. Okay. And it is given, or it is asked, that strike the wall at a maximum height, possible height. Okay. So let us suppose that the projectile traces something, the path like this, and this is the maximum possible height, and let us call this height as y. And the projectile is, suppose, launched with the velocity v0, and it is angle of theta with respect to the horizontal. And we can easily divide this v0 into two components, and this will be our v0 cos of theta, and this will be our v0 sine of theta. And in projectile, it is you can say very convenient or much more easier to understand that the horizontal velocity will be related with the distance covered in the horizontal direction, and the vertical will be with respect to the vertical direction. And for sake of convenience, let us assume that the distance between A and the wall is, suppose, x. We can later on replace this x by our L. Okay. So it means, for our, based on this, we can write the projectile equations. So we have our projectile equations, and the first equation will be our horizontal motion, for horizontal motion. So we are having horizontal motion, and the equation for horizontal motion, we can write that the distance we assumed is our x, and that is dependent upon t, and that will be equal to our horizontal velocity, that is our v0 cos of theta, and let us suppose the time taken to cover this horizontal distance is our t. Okay, so there this time t, it is going to travel horizontally in x direction, a distance of x, and same in time t, it is going to cover the vertical distance. Okay, so this is the correlation between the time t with respect to the horizontal as well as our vertical. And we can also write the equation for our vertical. So we can say that our vertical motion, and vertical is our y of t, will be equal to our its initial velocity in the y direction is our v naught sine of theta multiplied by t, and this was minus half gt square. And let us suppose this is our equation number 1 and this is our equation number 2. And equation number 1, we are going to put our x is equal to L. Therefore, we can write that our from equation 1, our x of t is equal to L. And therefore, we can say that our, so let me substitute it, we get our L is equal to v naught cos of theta multiplied by time t. And from here we can find out or write the equation for our time t. So we can say time t will be equal to our L v naught cos of theta. So during this time t, it is going to travel horizontally as well as in the vertical direction. And now we are going to substitute this value of t in our equation number 2. So we can say from equation 2, we get our y of t is equal to, this will be our v naught sine of theta multiplied by L v naught cos of theta, and this is our minus 1 by 2, and we have our g t square, that is L v naught cos of theta whole square. And we can solve it a little bit. This v naught cancels out, therefore we get that our y of t will be equal to our L, and this becomes our tangent of theta, and this will be minus 1 by 2, this will be with g L square, and multiply by 1 upon v naught square, and this is our cos square theta. Okay, and we can use, or rather we can say combine this 2 with our 2 cos square theta. Okay, and these 2 cos square theta we can write in terms of our secant theta as well as our tangent theta, basically secant square theta and our tangent of theta. So we get that this is equal to L tangent of theta, and here we have g L square v naught square, and we can write this our secant square theta multiplied by our tangent of theta. And one second, sorry, my mistake. That is basically, sorry, I messed it up. So we want that, let me come back to its original equation, that is our 1 by 2. We are going to keep it as it is and we are going to derivate it for our maximum. Okay. So we can say that for maximum height at wall, we are going to differentiate our y with respect to theta, and then we are going to put it equal to 0. Okay. Therefore, we get this as our dy by the theta will be equal to our L, and this comes as our secant square theta minus, and now we are going to get this will be our GL square upon V0 square, and this will be our cos square theta. Cos square theta is our secant square theta, and we get this as our secant square theta multiplied by tangent of theta. Okay. And we can take this, our L secant square theta is common, so this comes over L secant square theta, and this will be 1 minus GL square V0 square tangent of theta is equal to 0. Ultimately, for maximization, we are going to put it equal to 0. So this second function we can easily equate equal to 0, and this gives us that 1 minus GL square V0 square tangent of theta is equal to 0, or we can say that our tangent of theta, this will be our V0 square upon GL square. So this is our value of our theta, or we can say, we can find out, let me write it, and theta we can write as a tangent inverse. Tangent inverse V0 square, and we have this as GL square. And so this is the value of theta, so that the ball or projectile strikes at the maximum height. Okay. And in this case, there is another trivial part in this question, and which is basically that this value of this, the distance between the projectile and the wall, which is our L, it should be our less than our V0 square upon G. Okay. Because if it is not less than this V0 square of G, ultimately the projectile will be not able to hit the wall. So this is the constraint relationship between the distance from which the projectile is launched and the projectile velocity. Okay. So this constraint relationship is to be followed. Okay. And this also we can say that in terms of maximum range, we can write that this our L should be our less than the maximum value of the range. Okay. Then only this particular equation or solution is going to hold. So this is the constraint relationship between so that the projectile is able to hit the wall at a maximum height. So first question, and we come to the second question. And second question states that when a cannon is fired vertically upward, the projectile reaches a maximum height L. The cannon is then fired again with the same initial speed, but this time it is aimed along a smooth plane of a length L, inclined at an angle of theta to the horizontal. At what value of theta should the cannon be inclined so that the projectile covers the maximum horizontal distance d by the time it returns to the height of the top of the inclined plane? This statement is a little bit tricky, but solution is comparatively easy. So based on this statement, let us draw the diagram. So we have two parts in it. So in the first part, we fire a cannon in the upward direction directly. And the maximum height it reaches is our L. Okay. And then it is fired along an inclined plane whose length is our L. So this is our inclined plane, and this length is given as L. Okay. So basically we can say that suppose this is our cannonball, it is going to follow this length closely, and from here it is going to behave like a projectile. And it says that it should be coming back to the same height as that of the top of the inclined plane. Okay. So it starts from point A, becomes a projectile from point B, and ultimately it should reach the same height, that is our B prime, okay, at the same level. And this distance is given as d. Okay, so this is our first case, and this is our second case. So let us suppose that in the vertical direction it is launched with the velocity of v0. So same velocity v0 is given along the inclined plane. And if this angle is theta, so here also the angle will be over theta. And so for the first case, or we can say for vertical projectile, so you can say our first case, or we can say vertical projectile. And in this first case, we are going to use the conservation of energy. Okay. And it reaches a maximum height of L. So at the top, it is going to have only our potential energy, and that will be our mgl. And just after the launch, entire energy will be kinetic, that will be half m v0 square. So we can just equate it and solve the equation. Okay. So let us assume that this point is our P and this point is our Q. Therefore we can say that conservation of energy, we can say that the energy at point P should be equal to energy at point Q, or we can write this as a half m v0 square is equal to mgl. and we can easily cancel out our mass. Therefore we get that our V naught square is equal to 2gl. So this is the velocity at P, and same velocity will be in case second at point A. And for this second case, let us assume that the height of this point B is our h. Okay, so we can say our h is equal to L sine of theta. And it is going to, we can divide this V naught. So okay, let me, for case second, case, which is along the plane. Along the plane. And so we have a point A. So this is point A. The velocity is our V naught. Angle is our theta. So we get this is our V naught cos of theta, and we get this as V naught sine of theta. And this is our point B, and this point B is height of h, and this h will be equal to our L sine of theta. So once again, we are going to consider its vertical as well as horizontal component. Therefore, we can say that vertical motion and for vertical motion we can write that our this ball should be coming to the same height. So it should be coming as to B prime. So we can write the equation for our vertical, which in general we can say that is our y of t is equal to our initial velocity is V naught sine of theta times t, and this is minus half gt square. And our this y of t is nothing but our h, okay, because it is going to return back to the same height. So this is our y of t, and y of t is equal to h, and we know that our h is equal to L sine of theta. Therefore we can write this will be equal to our L sine of theta is equal to our V naught sine of theta times t minus half g t square. And we also know that our V naught square is equal to 2gl. So we have our two equations. Let this equation number 1 and this is our equation number 2. And solving this equation number 1 and 2, this will be a little bit lengthy, so I'm going to direct substitute. It will be quadratic in t, and therefore we are going to get that our t will be equal to our v naught by g, and it will be our sine of theta plus sine square theta minus sine of theta. And the distance between B and B prime is given as to us as d. Therefore, we can say that the horizontal distance is our d, which is our horizontal velocity v cos of theta multiplied by time t. Okay. And this is going to give us that our d will be equal to L sine of 2 theta. And what we need here is maximum. Okay, so we can just derivate our d and for our maximum. Okay, so we can say that maximum horizontal distance we can write that our d should be equal to our d max, and this will be only possible if value of our sine 2 theta is equal to 1, or we can say value of theta is equal to pi by 4. So this is our value of theta, for which we are going to get a maximum horizontal distance. So next question. It states that two balls are projected simultaneously from ground level to the points separated by a horizontal distance d. The ball on the right is projected vertically upward with the velocity v. At the same instant, the ball on the left is projected with the initial velocity u, chosen so that two balls collide exactly at the highest point of their trajectories. Determine the horizontal and the vertical components of the velocity u. For a given separation d, find the value of v for which the magnitude of u is minimum. And so we can just draw the approximate figure. So we are given there are 2 points, and let us suppose this is point A and this is point B. And from point B, this projectile is launched upward vertically with the velocity of v, and from point A it is launched at an angle with the velocity of our u.